All right, so we're going to start by looking at the questions that overlap with both of the papers, both of the tiers. So let's have a look at question 1. It says rubidium is found in group 1 of the periodic table, bromine is found in group 7. Rubidium and bromine react together to form an ionic compound. This would be rubidium bromide. Which row shows the correct electron change for rubidium and the formula of a rubidium ion? Well, if we know that rubidium's in group 1, that means it's going to lose 1 electron from its outermost shell. Bromine is in group 7, so it's going to gain 1 electron. Okay, note how I'm doing E- to remind us that an electron has a negative charge, so a charge of 1 minus. So for rubidium, we're going to be looking at it losing an electron, which means I can say A and B are wrong. And then because it's lost something negative, it has become positive. So it's Rb plus. So the answer is C. Question 2. Look at the diagrams of the electron structures for 4 elements. Which element is the most reactive? The first thing we're going to want to do is look at how many electrons there are in the outermost shell of each element, because that's going to tell us how these elements react. And in all cases but one, there's only one electron in the outermost shell. So A, B, and D have 1 electron in the outermost shell. C has 8. Well, we know that 8 electrons in the outermost shell, when it's the third shell, constitutes a full outer shell, and therefore C is not going to be very reactive at all because it already has a stable electronic configuration. Looking at B, C, and D, then we've got to think which way are they going to react? Do they need to gain or lose electrons? Because they've all got 1 in their outermost shell, they're all going to lose an electron. And we need to then think which is going to be the easiest for that to happen. It's going to be the one that has the largest atomic radius and the most inner electrons, okay, because those inner electrons are going to be shielding that outer electron. So A has the most electrons in between the outermost electron and the nucleus, which means it's going to be lost very, very easily, and therefore it will be the most reactive. If you were stuck for this question, another thing that you could do is you could count the electrons and then look at which elements have those number of electrons as their atomic number, and identify it that way, because we know that the further down group 1 you are, these are all in group 1 because they've all got 1 in their outermost shell, the further down group 1 you are, the more reactive the element is. Question 3. Which statement is correct for a group 1 element? It dissolves in water to form a bleach. No, that's a group 7 element that does that. It's a non-metal. No. If you look in group 1, they are all metals. They're on the left-hand side of the periodic table. It's an inert gas. Again, no, that's going to be group 8 or group 0, the noble gases. It reacts with water to form hydrogen. Yes, and a metal hydroxide. Okay, so we need to know both of those. So the answer is B. Question 4. Magnesium is a more reactive metal than copper. Why? Well, they're both metals, so in order to react, they lose electrons. If they're losing electrons, we just need to think which of them does that more easily. Okay, so let's look at the options. Copper forms positive ions more readily than magnesium. No, because if it did, then copper would be more reactive than magnesium. Copper is higher in the reactivity series than magnesium. No, again, that would mean it was more reactive. Magnesium gains electrons more readily than copper is wrong because it's about losing electrons. So the answer is D. Magnesium loses its outer electrons more easily than copper. Note how I'm using capital letters for all of my answers so that there's no ambiguity about the letter that I've written. Which statement about halogens, group 7 elements, is correct? Astatine is the most reactive halogen. Well, this is wrong because astatine, if we have a quick look at the periodic table, it's at the bottom down here, and we know that in group 7 the reactivity gets less as you go down the group. Chlorine has the electronic structure 287, or let's have a look. So the number of electrons in chlorine is 17. So you'd have 2, 8, 7 adds up to 17. So that is correct. Let's just have a look at the others so that we know why they're wrong. Fluorine is the element with the darkest colour. No, it's pale yellow and it's a gas. The halogens have the molecular formula B3, oh sorry, X3. No, they've got the formula X2. How does a catalyst speed up a reaction? It decreases the activation energy. Yes, it provides an alternative reaction pathway with a lower activation energy. It doesn't change the energy of the reactant particles, definitely not. It doesn't make the activation energy higher, because if it did, then the reaction would be even slower. And it doesn't change the actual energy of the reactant particles. So the analogy that I always use for this is it's like telling people that there are loads of sweets upstairs that they can go and get for free. Some people will go up because they'll have enough energy to climb the stairs. If you then tell them that they can get a super fast lift up the stairs, then a lot more people are going to be able to go and access those sweets, because the lift means that they can get to the sweets without putting in any extra energy. So without having enough energy to go up the stairs, they're still able to get them. So the lift is like the catalyst there. We haven't changed the energy of the people, like we haven't changed the energy of the reacting particles. Right, question 7. This question is about the reactivity series of metals. A student heats mixtures of metals and metal oxides. Look at the table, it shows his results. So we've got this table here and it says, using the results, work out an order of reactivity for the metals. Explain how you use the results to put the metals in order of reactivity. So what's happening here is we've got a metal and a compound of a metal. So a metal plus a metal compound. Okay, and we're trying to see if it reacts. Okay, if it does react, then let's say that this is metal A and this is B. So if we do get a reaction, that means that A is more reactive than B, because this is a displacement reaction and A has displaced B because A is more reactive. If there is no reaction, then that means that B is more reactive than A, because B is already reacted, it's happy to be in its reacted state, and A is not sufficiently reactive to displace B from its compound. So if you look at this, copper has no reaction with any of the other metal compounds. Okay, so we've got our metals at the top, because they're the ones that are by themselves, and we've got our metal compounds down the side. So because the copper has not reacted with anything, we know that copper is going to be at the bottom of our reactivity. Then we want to look at the one that reacted with everything apart from its own metal. And if we look at magnesium, it had a reaction with the copper oxide and the lead oxide and the iron oxide. So the magnesium is at the top. Okay. Now we need to just look at lead and iron. Well, lead only reacts with one, so it's only more reactive than copper. Iron reacts with both the copper oxide and the lead oxide, which means that iron is second, and then lead is in between the iron and the copper. And so we've got to talk about what's going on here. So a more reactive metal will displace a less reactive metal. So let's talk about magnesium. So magnesium displaces all other metals from their compound. Okay. And then we also want some kind of explanation about how the lead can be placed relative to the iron. So we can also say the lead is less reactive than iron as it was displaced by iron from lead oxide. But it displaced copper. From copper oxide. Okay, now you need kind of two statements to explain how you placed your metals in their order of reactivity, and you need to have a totally correct order of reactivity. So in terms of the marks allocated, you get 1 mark for having your magnesium at the top and copper at the bottom. You then get a 2nd mark for having iron and lead in the correct order in the middle, and then you get your final 2 marks for some explanation. So there are other explanations that would be acceptable. So you could also talk about why you know that copper is the least reactive, for example, but this kind of summarizes most of the information we need. In another experiment, the student reacts copper with silver nitrate, AgNO3. Silver and copper nitrate, CuNO3, are formed. Write a balanced symbol equation for the reaction. So let's first of all identify our reactants. So the student reacts copper with silver nitrate, and then they tell us that silver and copper nitrate, I'm going to highlight the formulae, are the ones that are formed. So my reactants I've got highlighted in yellow, and my products I've got highlighted in green. The formula for copper, we just need to use our periodic table or use what we've been given above. So they've given us Cu up here, but we can also look at our periodic table, find copper over here with Cu, and silver is below it with the symbol Ag. So copper plus AgNO3 goes to silver, which is just Ag, plus Cu brackets NO3 close brackets 2. It's really important that you copy everything properly, that you've got only capital letters for the starts of your elements. So the U and the G in copper and silver must be lowercase, otherwise you will lose marks. Now, if we're looking at whether it's balanced, you can see that there are 2 nitrate ions on the product side, so NO3, 2. So because I've got just 1 lot of NO3 on the reactant side, I'm going to balance my AgNO3 by putting a 2 in front of it. So that's balanced my NO3. But now I've got 2 silvers on this side and only 1 on my product side. So I'm going to balance it by putting a 2 there. And that gives me the balanced equation. Question 8. A student investigates the rate of reaction between marble chips and hydrochloric acid. Both experiments use 50 centimeters cubed of hydrochloric acid and an excess of marble chips. This is a key word. Okay, so the excess of marble chips means that my acid is the one that's going to be used up. So the acid will be used up, and I'll have chips left at the end. He measures the total mass of carbon dioxide given off for different sizes of marble chips. Look at his results. So we've got time in minutes, and then we've got the total mass of carbon dioxide given off for large marble chips and small marble chips. And we've got the large marble chips plotted on here. It says the student has plotted his results for the large marble chips on the graph, plot his results for the small marble chips, and draw a line of best fit. So the small marble chips, let's have a look. So at 4 minutes, there are 0.8 grams of carbon dioxide given off. So I'm going to zoom into this. 0.8, so 4 minutes is here. And it helps because as all of the times were taken identically, we can actually just go up on the line that our cross was made for the large marble chips. Then we need to look at what the intervals are on the y-axis. Because 0.5 is every large square, that means each small square is worth 0.05. So 0.8 would be, so that's 0.6, 0.7, 0.8. Okay, make sure that you plot these points accurately. Then 1.4 at 8 minutes. So here's my 8 minutes. 1.1, 2, 3, 4 up here. Okay, that's not the best. I might redo that one. Okay, this is why you do it with a pencil so that you can accurately go through the points. 1.6 at 12 minutes. So there's my 12, 1.5, 1.6 over here. And then 1.7 to the end. So that's 1.7, 1.7, 1.7. Okay, now drawing the line of best fit is going to be really difficult for me to do on the screen. I'll have a go. You can probably notice, especially if we look at the large marble chips example, that the line is pretty much straight for the first few points, and that's the same for us. So if you'd rather do your first bit with a ruler and then curve off when we get from about sort of 8 minutes onwards, that's absolutely fine, because it is pretty straight through that part. So I'm going to have a go. I can't use a ruler, obviously, and I'm going to have to take my hand off. Okay, so ideally that would be less shaky, but for benefit of the doubt and the fact that I'm doing this on a graphics tablet, I think that would be enough to get me the marks. So we've done part 1 and part 2. Look at the line for the large marble chips. How long does it take for the reaction to finish? Well, this means how long does it take for us to stop getting any more product? Okay, not how long we measure it for. So let's have a look at the graph, or we could just look at the results. We can see that it stays the same after 20 seconds, which means that by, 20 minutes, which means that at 20 minutes, the reaction has finished. Okay, so 20 minutes. What mass of carbon dioxide is given off after 15 minutes? We're still looking at the large marble chips one, so they're asking if we can read off the graph that they've plotted. So 15, going to get a straight line if I can. I don't know if I'll be able to get it to line up. Let's see. Thereabouts. Okay, so it crosses at 15 minutes, and now I just need to read off there. Okay, so as we said, each one of those is 0.05, so that's 1.45. Okay, if you wanted to count up, you could go 1.1, 1.2, 1.3, 1.4, and then that must be 1.45. Okay, so 1.45 grams is what's been given off after 15 minutes. The reaction is faster with small marble chips. Write down 2 ways that the graph shows this is correct. Well, firstly, we've got the gradient being steeper. And secondly, we can see that it reaches the maximum volume of gas at an earlier time. Okay, so it finishes earlier. So the gradient at the start is steeper. And then secondly, the small chips reaction finishes faster. And if we want to do even better, we can actually say when it finishes. So it's finished at 16 minutes instead of 20. Then it says both small and large marble chips give off the same mass of carbon dioxide at the end of the experiments. Explain why. Well, that's because we use the same volume of the same hydrochloric acid. So both experiments used 50 centimeters cubed of hydrochloric acid, and we were told that it was an excess of marble chips. So we shouldn't refer to the marble chips here. We should just say that both experiments used the same volume of acid. Okay. Then part E, it says a balance was used to measure the amount of carbon dioxide given off. Write down the name of a different piece of equipment that could be used to measure the amount of carbon dioxide produced. So carbon dioxide is a gas, therefore we could also have used a gas syringe, and the spelling of that is SYRINGE. So be careful with your spelling. It's easy to get the Y and the I mixed up or the wrong way around. Then question 9, a student investigates the rate of reaction between magnesium and hydrochloric acid. The reaction gives off hydrogen gas. So we've got the little diagram there, but doesn't look finished to me. So the student wants to investigate how changing the concentration of the hydrochloric acid affects the rate of reaction. Look at her plan. First experiment, I'll put 0.5 grams of magnesium ribbon into the flask. I'll add 50 centimeters cubed of hydrochloric acid. I will measure how fast the gas is given off. Second experiment, I will put another 0.5 grams of magnesium ribbon into the flask. I will add 100 centimeters cubed of the same hydrochloric acid. I will measure how fast the gas is given off. Another student thinks that the plan will not work and he does not understand exactly what he has to do. Suggest how the plan for this investigation can be improved. So there's quite a lot that's not quite right with this. So when it says I will measure how fast the gas is given off, there's been no description of how you're actually going to do that. The other thing, and this is very important, we've been tasked with looking at how changing the concentration of the acid affects the rate of reaction, but they're going to use the same hydrochloric acid, so they haven't changed the concentration. All they've done is change the volume, and so that's not going to affect the rate of reaction. Okay, changing the volume of the acid does not change the rate of the reaction. All right, so the reaction needs to be done for the second time using a different concentration, but same volume is preferable because we haven't been given any information as to which is in excess. So we want to make sure that hopefully the magnesium is the one that's the limiting reactant. The hydrochloric acid is in excess, and so we won't run out. So let's just talk about what we're going to do then. So we need to change the student must use a different concentration of acid in the second experiment, which I'm abbreviating to EXPT. Changing the volume will not affect the concentration. Okay. The plan needs to tell us how we're going to measure the gas. And we also need to know how fast it's going to be happening. So the plan needs to say how to measure the gas volume and the rate at which this changes. Okay. So we can then suggest how we could do this. So use a gas syringe, e.g. use a gas syringe to measure the volume of gas and a stopwatch to do this, to do so at regular intervals, e.g. every 10 seconds would be a sensible one to do. Another thing that we need to make sure is the same. If we are investigating the concentrations effect on rate, then we need to keep all of the other things that can affect the rate of reaction constant. One that we can talk about quite simply here is to make sure that the temperature is the same each time. There's lots and lots of ways you can score marks on this question. So if you have a look at the mark scheme afterwards, you can see whether any ideas that you had that I didn't mention might have given you credit as well. Question 10. It says, a student adds some magnesium to dilute hydrochloric acid, HCl, magnesium chloride, MgCl2, and hydrogen gas are formed. Write a balanced symbol equation for this reaction. So again, I'm going to highlight products in green and reactants in yellow. So we've got reactants Mg and HCl. Note how I'm really making sure that my L for the chlorine is lowercase. Goes to MgCl2, and hydrogen gas, the formula for that is H2. And I've got one magnesium on my reactant side, one on my product side, so the magnesium is fine. But I've got one hydrogen on my reactant side and two on my product side, and I've got one chlorine on my reactant side and two chlorines on my product side, so I'm going to need 2 HCl, and now my reaction is balanced. She wants to investigate how changing the concentration of hydrochloric acid affects the rate of reaction. The student uses hydrochloric acid with a concentration of 1 mole per decimeter cubed, magnesium ribbon, a conical flask, a measuring cylinder, a mass balance, and a stopwatch. Identify the independent variable in the investigation. Well, the independent one is the one that I change. So I change the independent variable. Okay, so what are we changing? We are changing the concentration. It literally says it there. So I change the concentration, therefore the concentration of the acid is the independent variable. Identify 2 control variables in the investigation. A control variable is one that you are in control of so that it does not change. So the control one, you keep it the same. You keep it constant. So just as before, we're investigating changing the concentration. So think about the other things that could change the rate of reaction. We don't want them to affect the rate of reaction, so we want to control them. So it could be temperature, okay? We do not want the temperature to affect the rate of reaction. We are reacting a solid with a solution. We know that another thing that can affect the rate of reaction if you've got solids is the surface area to volume ratio. So we want to make sure that we keep the surface area to volume ratio of the magnesium the same as well. Right, question C. The student measures the time it takes from adding magnesium to the hydrochloric acid until the reaction mixture stops bubbling. The table shows the student's results. The results at 0.75 moles per decimeter cubed are not precise. Suggest one reason why this might have happened. So precision is about being close together, so they are not close together. Okay. So let's have a look. We've got 65, 55 and 41. So they're really quite spread out. Okay. Now suggest one reason why this might not have been close together. So one reason why it might have happened. So you just need to think about what we're doing in this reaction specifically, in this experiment specifically. It's not good enough to just say she made a mistake, she did something wrong, because that doesn't tell the examiner that you understand what happens in this particular experiment. So you could have something like you didn't reset the stopwatch, okay, so the stopwatch might have not been reset. Or we could have not washed out the equipment properly. So if we hadn't washed out the equipment properly, and maybe we'd left a load of water in the conical flask, for example, that would mean that when we then added the acid's concentration would have been diluted if there was still water in there. So the equipment not washed out properly. Okay. Or we might not have stirred it properly, or we might have accidentally added the wrong mass of magnesium, something like that that's about this particular reaction experiment. Part D, the results at 0.75 moles per decimeter cubed are repeated. This is a graph of the student's results. So we've got time on our y-axis because this time they were measuring the time taken for the reaction mixture to stop bubbling. So it's not how we normally do it, where we're measuring the volume of gas given off over time. We're saying this is the concentration that we chose, and we're looking at how long it took the reaction to stop. Okay. What conclusions can you make from these results, and include ideas about particles in your answer? So let's start off with the conclusion from the graph. So as the concentration increases, so we always want to start with as the x-axis changes, something happens to the y-axis. So putting this in, we're going to say as the concentration increases, the time decreases. Or the time taken for the reaction. Okay, so because the time is getting shorter, that means the reaction is getting faster. Okay, so reaction gets faster. Now we need to do our little explanation. So when we increase the concentration, we are changing the number of particles per unit volume, and we're making that number bigger. Okay, so higher concentrations have more particles in the same volume. Okay, more particles for the same volume. Therefore, basically you're making it so that stuff is more crowded, okay, and therefore you're going to have a higher frequency of collisions. So more particles in the same volume, so collisions are more frequent. And we've got to say something about time. Collisions are more frequent, collisions happen more often, there are more collisions per second. Anything that says that in a certain time you will have more collisions, because we have no idea how many collisions are going to occur in total. It might be that when we had a lower concentration, if something else had gone wrong, there might be a sort of greater total number of collisions overall, but that would take a much longer time than getting a smaller number of collisions overall, but they occur in a very short space of time. So it's the frequency that's important. Okay. Right. The next question then, question 11. Local councils collect waste from households. The graph shows what happens to waste between 2001 and 2017. Describe and explain one trend shown by the graph. So let's have a look. So we've got dark is other, so I'll mark them off on the end. So this is other. Our slightly paler grey is landfill. Our dotted one is burned for energy. And our pale grey is recycled. So the burning for energy has increased over time, landfill has decreased over time, other whatever that is has slightly increased, and recycled has increased up to a point maybe around 2010-ish, and then kind of stayed fairly constant. So we want to do our description and our explanation of one of those. Probably the easiest one is to talk about why landfill has decreased. So we can either use the information on the graph to link it together, or we can use our own knowledge. So let's say the less waste is sent to landfill, and then you can either say because more is recycled or more is burned to produce energy, or we could then talk about the public are more aware of recycling. So that's using our sort of extra knowledge. So landfill use has decreased, or less waste is sent to landfill as more is burned for energy or recycled. Okay. State one disadvantage of recycling. There's loads and loads of potential things that we can talk about. Separating the materials is difficult, so the waste needs to be separated. Another thing you could say is that it's expensive, or that everything needs cleaning, or it's time consuming, or you use energy in doing it, or you need to collect or transport it, or the quality of the material deteriorates, which is true for some things, but not for everything. So this concludes all of the questions that are in both the foundation and the higher tier section.